The summary regarding the last two videos is that the ideas that we presented there extend generally to linear, non-homogeneous recurrence relations with constant coefficients as we describe in the theorem. If A sub n h represents the general solution of the recurrence relation I've underlined here, linear, homogeneous, constant coefficient, and that is homogeneous, and A sub n super p is any particular solution, any single particular solution of the non-homogeneous counterpart, where we have the non-homogeneous part here, then an equal the sum of the homogeneous solution, which will have arbitrary constants in it, and the particular which will not have arbitrary constants in it, is the general solution of the non-homogeneous relation. So that's a way that we can put things together as we have been doing. Now I'm going to scroll down here to a summary of the different types of non-homogeneous pieces that you'll be looking for, the particular solutions. So the theorem here summarizes some of the things we've been saying as well. The form of a particular solution of a non-homogeneous recurrence relation, an is can minus 1 plus can minus 2, etc., out to ck an minus k plus the non-homogeneous part right there, is given below for the stated cases, and so I'll summarize them in a table. The notation p sub l stands for a polynomial of degree L. The notation q sub L likewise represents a polynomial of degree L, and they're polynomials in n. That's a variable rather than x. In general, the solution in the third column here, the third column that I'm mentioning here, will have coefficients in them that have to be determined by substituting the proposed solution into the equation, as we have been doing in the examples above. So here's what the table summarizes. So this is based on what the characteristic root is, and the first couple of cases we've kind of looked at, and I thought I'd pull them out ahead of time. If one is not a root, and the fn above here in our equation, the non-homogeneous part is a polynomial in n of degree L, that may be a constant or a linear polynomial or higher order, then the particular solution will be a polynomial of degree L as well. Right? So that's what that means. It'll be a different one. That's why I'm using a q there instead of a p. So a polynomial of degree L in n, you use a polynomial of degree L in n as well for your particular solution, where all the coefficients, degree L would have L plus 1 different coefficients, have to be determined by using the equation to see what those would be, using the recurrence relation. That's if one is not a root. If one is a root, then if one's a root, that means constants are solution, as we'll see in an example coming up. And in fact, if it's a multiple root, then n and n squared and so forth, those sequences may themselves be solutions. So the particular solution has to be modified slightly from what we have above. From given a polynomial here, we have to take a polynomial of degree L, but increase its degree by multiplying by n to the m, where m is the multiplicity. M is the multiplicity of the root 1. In general, if we go to the power example, if the non-homogeneous part is a power, like so, and b, the root or the base of that, is not a root of the characteristic equation, then we can just try a multiple of that power. This generalizes to a power times a polynomial as a non-homogeneous part, and we'll see that below right here. There's one right there where we have a power and then we have an n, so a polynomial in n. Then the particular solution will have the same sort of form as long as b is not a root. If b is a root, then you have to do something like we did in the case above here. You have to multiply your potential solution by the nth power of n. That, it looks a little complicated. We'll do some examples to show how this works out. So in the first case here, we'll look at this one right here, where we have an equals 4 an minus 1, just first order, and the non-homogeneous part is 5n times 3 to the n. So what the above would say is that in that case there, the 3 is not a root of the characteristic equation, because r in this case is 4, not 3. Right? So we're in this situation right here. We're in this one right here, actually, the second line of that sort, because we have a polynomial here, and that's a degree 1. So the particular solution is going to have the form c plus dn times 3 to the n. Okay, a polynomial of the same degree as that right there, and then times 3 to the n. Notice I'm not carrying the 5 down here. That'll be taken care of by the constants c and d as we figure those out. So if you substitute that in, and we'll see how far we get before we get a little bit too bored with doing all of this. Let's just see. So if that's our potential here, then an in the equation, looking up here at an, for this anp, for the particular solution, would be c plus dn times 3 to the n is equal to 4 times, now an minus 1 would be c plus dn minus 1 times 3 to the n minus 1. Okay, so that's just, I've changed that now to an n minus 1 here, and that to an n minus 1 here. And then we have plus 5 times 5n, times 3 to the n, like so. So what we're going to do here is cancel a 3 to the n minus 1. So 3 to the n minus 1 is a highest power of 3 we could cancel. So that would leave us with 3 times c plus 3 dn is equal to 4 times c plus 4 dn minus 1. There's no factor of 3 there. There is a factor of 3 here that I put in. And then plus 15n, because one factor of 3 over here survives. So that's just a matter of solving that. And if you solve that, I'm not going to go through it, but you can find c and d. Again, you're going to equate coefficients of common powers of n. So in other words, we would calculate or collect the constant parts here, which would be 3c minus 4c if I bring this over, plus 4d. Do you see where I got the 4d? 4d times minus 1, but I'm adding that to both sides. That gives us the constant part, I think. And then we have plus 3dn minus 4dn is equal to 15n, like so. And I guess this isn't too horrible to solve. You see right here we have minus dn is 15n. That's the parts that involve n. So that would say that d is equal to minus 15. And if we put that over in here, we're going to get that c is equal to minus 60. So put this over here, and we see c is equal to minus 60. Right, because this has to be, what does that have to be equal to? Well, that has to be equal to 0, because there's no visible constant part over there, right? The constant part's 0. Right, okay, so that would tell us that the solution is an is equal to, the homogeneous is alpha times 4 to the n, because of the 4 up here, plus, it'd be minus 60 times 3 to the n, minus 15 times n 3 to the n, like so. So I guess I did it all just to show that. Maybe that's good to see one done like that. This one here, 2, is a very curious one. Seems pretty simple, but in fact this case here, if you looked at the characteristic equation for the homogeneous part, it's just r is equal to 1. R is a root, and what that says is that if you put in any constant here that we might try to use here, a to the n equal d constant won't work. Right? Why? Because if you put it in there, you get d is equal to d plus 6, or 0 is equal to 6, which I think between me and you, that's not going to work. So what the table says, let me scroll back up there and we'll see it, is if 1 is a root, then we have to kick up the power of the polynomial. Our polynomial is just a constant. Kick up the power of the polynomial by n raised to the multiplicity of 1 as a root. Well, it's just 1 in this case. So here we'd rather try a n p. So this didn't work. A n p is equal to d times a constant. I'm sorry, n times a constant d. N to the first relates to the multiplicity of 1 as a root of this characteristic equation. That's just 1. So dn would work here, whereas d itself would not. And in that particular case, it is actually 1 times n. D is equal to 1. So if you put that in there, you get dn is equal to dn minus 1 plus 6. I'm putting that into the original equation now, into the original equation, and solve for d, and that simplifies real quickly. The dn's cancel and you get 0 is equal to minus d plus 6, so d is equal to 6. So we get an is equal to, well, alpha times 1 to the n, because r is equal to 1, plus 6n, or maybe more simply just alpha plus 6n, and an, or the alpha, I'm sorry, is an arbitrary constant.